Okay. We'll talk about learning when the training set is not IAD, but rather we assume that there are weak correlations between the training samples. In particular, we'll assume that the training set satisfies what's called Dobrushin's condition, and we show that we can learn under this condition. And the second result, so we show a uniform convergence bound under a stronger condition. So what is the Dobrushin's condition? So this is a condition on a random vector this condition says that the entries of this vector are only weakly correlated. So each entry we'll think of as a node in some correlation graph. And we will define some influence notion between different nodes. So the influence between node I and node J will roughly be the extent to which the value of the I can affect the conditional distribution of Zj. And the larger the influence is, the higher the nodes influence each other. And the Dobrushin's condition states that each node has a bounded total influence. So no node can have too much influence on the others. And if the Dobrushin's condition holds, then there are many IAD-like properties that hold, as Chernoff type inequalities and more. So here are some examples of models satisfying the Dobrushin's condition. So the first one is actually taken from physics. That's like the motivation for defining this model. So you have atoms on some lattice, and each atom can have a spin. The spin can either be positive or negative, and neighboring atoms are more likely to have the same spin. So, but if the Dobrushin's condition holds, then, so although like in the micro level, it's not going to be IAD, still like in the macro level, this random variable will behave as IAD, like it will have IAD properties and the Dobrushin's condition will hold. And the second example, so this is a CS example, so here we have a social network, and each person has a different opinion, like has a different favorite TV show. And while friends tend to have a higher probability of favoring the same shows, still, if the correlations are weak enough, then we can say that the Dobrushin's condition is going to hold, and the samples are going to be roughly IAD. And I just want to say that the Dobrushin's condition may be sometimes too strong to hold in practice, but we hope in future work to build upon this result and show bounds for random variables which are highly correlated. Okay, so this is the result on learnability under the Dobrushin's condition. So we have some training set of examples. And now these examples are, rather than being IAD, they are jointly Dobrushin. And the second simplifying assumption that we make is that each of the marginals is drawn from the same distribution, and we want to learn with respect to this distribution. And what we show is that the sample complexity is nearly the same as the sample complexity for IAD, for learning with respect to these Dobrushin samples. Okay, so how do we prove this? So we use the notion of sample compression schemes. This is a notion that characterizes algorithms that the output hypothesis depends only on a small subset of the training data. For example, the support vector machines, the output hypothesis depends only on the support vectors. So this is some kind of a sample compression scheme. And there's been a lot of work on them. And we show that any sample compression scheme will generalize under Dobrushin's condition. And now, since for any class of finite VC there exists a sample compression scheme algorithm, then we can learn any class of finite VC. And we actually have a more general lemma, which is not technically difficult, that characterizes like when sample compression schemes work, or it gives sufficient condition for sample compression schemes to generalize. So that's about the result of learnability. And now, what if we want to prove uniform convergence? So we didn't manage to prove this result for the Dobrushin condition, but if we assume a slightly stronger condition, then we can show uniform convergence under essentially the same IAD sample complexity. So we bound like a supermom over all hypotheses in the class of the test error minus the training error, and we bound it by the Gaussian complexity. This is like the same notion that appeared in the previous talk. And so while in the IAD case, this supermom is bounded by the Rademacher complexity, here we bound it by the Gaussian complexity. And as I already said, like these two notions are almost equivalent up to some small factor. And I just want to say that this stronger condition includes high temperature pairwise Markov random fields, for those of you who know this definition. And here is a main idea of how this result is proven. So we write this supermom of training versus test loss. And this can be bounded by some kind of Rademacher complexity. But when the signs are, rather than being IAD, they are weakly correlated. But since they are only weakly correlated, we can use the majorizing measure theorem of Fernick and Talleyrand to replace the weakly dependent sign with IAD Gaussians. And then you get the Gaussian complexity. So yeah, so we bounded the supermom by the Gaussian complexity. And just relating to prior work, so there has been a lot of prior work under similar models, but as far as we know, other relevant the very similar models are only about time series data, where the correlation structure is assuming the samples come from some time series, but network correlations do not satisfy this assumption. So that's how we generalize over this. Okay. Yeah, there is some parameter alpha in the Dobrushin condition, and the sample size increases by a factor of 1 over 1 minus alpha. And this factor appears in many other bounds. Yeah. This actually can sometimes destroy the Dobrushin condition. But yeah, there are some way to weaken this assumption, but yeah, I didn't talk about it. Yeah.